Okay, so in this video, we're going to take a look at some example moment calculations. So before we get started on that, something a little bit different. This system is stationary, which means everywhere on the system, the moments are balanced out. So what I'd like you to try and do is have a go at figuring out what goes on the question mark here to ensure that this system is completely balanced, so that this system will not move or rotate at all. So pause the video, have a go, see if you can figure it out, and then we'll go through what the solution is. Okay, so let's take a look at how I solved this problem. So the first thing I'm going to do is I'm going to focus on this beam at the bottom. So I said the system is completely stationary, so therefore this beam at the bottom must be balanced. So first thing I'm going to do is turn it into a force diagram and also put in the pivot and make it look like something you're a bit more familiar with. I've made it look like a seesaw. So you can see there's the string that it's hanging on is the pivot, and this point will be stationary even if the object rotates. And Y I've put in is the weight force of the yellow bird, P is the weight force of the purple bird. So you can see I've put those in acting downwards. Okay, so next, because it's stationary and not rotating, we're going to look at moments of the forces. So just a refresher, we should know that the moment is the product of the force and the distance perpendicular to the force. So because all the forces are vertically downwards, the distances are all going to be horizontal and measured to the pivot. And so this force we can see labeled in here is making the system rotate clockwise. The Y force on the other side will be making it rotate the other way. So if this system is stable and is not rotating, what that means is the moment clockwise is equal to the moment anti-clockwise. So we can calculate the total moment clockwise. It'll be 1 times P plus 2 times P, because the second P force is 2 units from the pivot. The moment going anti-clockwise will be 1 times Y plus 0 times Y, because one of the weight forces is acting at the pivot, so it doesn't have a moment. And then what we can do is we get this expression Y equals 3P. So we know the weight force of one yellow bird is equal to 3 purple birds, and we're going to use that in a second. So now we're going to focus on the top section here, and again we're going to turn it into a force diagram. So the thing people often miss here is that we've got the weight force of all of the birds at the bottom acting through the point on the left there. And I've replaced the yellow birds each with 3 purple birds, because that's what we already figured out. So anywhere you see a yellow, I've replaced it with 3 purple birds, which is why there's a total of 8 birds acting on the point 2 units from the pivot. So the moment clockwise here would be 2 times 3 plus 3 times 3 plus whatever 1 times whatever goes on the question mark. So we've got 15p plus question mark. The total moment anti-clockwise is 8p times 2, so 16p. And we know it's stationary, so we know those two are equal to each other. So we know that the question mark should be a purple bird. That's what would make the system balance. Okay, so that's a bird balancing problem, and you can find these in newspapers on the puzzle page quite a lot if you want to practice these to practice your moments. But let's have a look at some other problems as well. So we're still going to focus on balancing type problems and finding out where some unknown thing goes. So in this section, what we're trying to figure out is where we put the 4 kilogram mass to make this system stationary. So pause the video, have a go at trying to figure out the answers to these questions, and then we'll go through them to finish off. So pause it now. Okay, so let's start going through these questions. So first of all, we're going to work out the total moment going clockwise. So the 2 masses on the right, their weight forces are going to be acting to make the system rotate around. So that's what we can put on there. We've got these 2 acting this way, so they would described as clockwise moments. So the 1 kilogram mass is 2 units away, and the 2 is 3 units away. So what we're going to do is we're going to first turn the mass into a weight force by multiplying it by 10 10, and then we're going to multiply it by the distances, so it's 2 and 3 for each of the forces, giving us a total moment of 80 Newton meters going clockwise. Okay, so what we can do is we can then use that to figure out where we need to put the 4 kilogram mass. So first of all, we know the weight force of this object is 40 newtons, and we need the moment to be 80 Newton meters. Therefore, we need to put it 2 units from the pivot, and we get a distance of 2 meters, and it will be on the left-hand end of the beam. The last thing we're going to try and figure out is what the contact force acting upwards from the pivot must be in order for this system to be stationary. So we are going to add up all the weight forces of the masses, and we're going to assume the beam doesn't have any mass because we haven't been told that it does. So therefore we can get the contact force acting upwards at the pivot must be equal to the weight force if it's stationary, which must be 70 newtons, as we can see there. Okay, so let's have a look at a slightly different problem. Okay, so we've got another type of balancing problem, and this time we're trying to figure out what mass we should place on A to make the system balance. So we're going to approach it the same way. So I'd like you to pause the video, have a go and see if you can solve what goes on A, and then we'll review it so we can check. Okay, so let's start our review. So first of all, looking at the clockwise moment. So we've got 3 weight forces that are going to provide a clockwise moment. The 4 kilogram and the 2 1 kilogram masses. And the 4 kilogram is 1 meter away. The 1 kilogram masses are 2 and 3 meters away respectively, giving us a total moment of 90 Newton meters. Then what we can do is we can start trying to solve what we put on A. So first of all, we need to find out what the anti-clockwise moment of the 2 kilogram mass is. So it's 3 units from the pivot, so its moment is 60 Newton meters. So therefore the moment of the object we put on A must be 30 so that the moment's balanced. Then we know it's a distance of 1 meter from the pivot, so we know that we should put a force of 30 newtons downwards at A, which means we need a mass of 3 kilograms at A. And then to finish off, just like we did before, we want to know what the contact force upwards must be. And that's what we've calculated here. I've turned all the masses into weight forces by multiplying them by 10. Then we're just going to add them all together, and it gives us 140 newtons once we add them together. Okay, so now what we're going to do is we're going to have 2 unknowns that we're putting in this one. So what we're going to do is you've got a 4 kilogram and a 1 kilogram mass, and we need to therefore determine where to place these 2 masses to make the system balance. So again, pause the video and have a go, and then we will review it once you've had an attempt at the question. Okay, so let's first work out what the clockwise moment is. So that's what I'm going to do first of all. So I've turned all the masses into weight forces, multiply them by the distances. It gives us a total of 130 Newton meters. So what I'm going to try first of all is put the 4 kilogram mass 3 meters from the pivot, so on the left-hand end, and that gives us a total moment of 120 Newton meters. Therefore, we can put the 1 kilogram mass 1 meter from the pivot to give us the remaining 10, giving us a total anti-clockwise moment of 130 Newton meters. This, I think, is the simplest solution to this problem. There are probably other solutions which give you horrible distances, but this is the simplest one to this problem. Okay, so the next one, we're going to think about balancing meter rulers with different forces acting on it. So the challenge with these questions is going to be first constructing a diagram of what this looks like. So previously I gave you the diagram, now you need to construct it yourself, and then you're going to be applying moments to see if you can figure out the problem. So for each of the questions, first of all, try and draw a diagram what it looks like, then try and solve it using moments. So I'll give you a second to have a go at this one. So pause the video and have a go, and then we'll review what mine looks like. Okay, so let's first turn this into a diagram, which is what you can see here. So we've got 3 Newton force upwards at the 20 centimeter mark, which you can see on there. F is acting at 70, and the pivot is placed under the 50, so at the middle of the ruler. So the 3 Newton force is 30 centimeters or 0.3 meters from the pivot. F is 0.2 meters from the pivot. So then what we can do is we can multiply 3 by 0.3, divide by 0.2. That tells us the force must be 4.5 newtons upwards. Okay, so let's have a look at another one. So same scenario, but with different forces acting on it. Again, see if we can draw a diagram and solve it. Pause the video now and have a go, then we'll review the answer. Okay, so this is what my diagram looked like. It's 5 newtons and it's 0.4 meters from the pivot. F is 0.1 meters from the pivot. Make them equal to each other and then divide both sides by 0.1. We get a 20 Newton force upwards at as F. Okay, so a few more of these. The pivot's still in the same place, so we've got a few forces acting on it now. Again, have a go at this question so then we can review it. Okay, so this is what my diagram looks like. So we've got the 5 Newton at the 5 centimeter mark. We've got 12 newtons downwards, 10 centimeters from the pivot, and F upwards, 25 centimeters from the pivot. So first of all, we weren't told which direction F acts in, so I just took a guess at it and put it upwards. If the calculation gives us a negative number, what that will tell us is we put F the wrong way up to start with. So that's not necessarily a problem. So the 2 moments going anti-clockwise are F and 12. We can see that they're rotating it in the same direction. The only one going clockwise is the 5 Newton one. So that's what we've put into the calculation. So 5 times 0.45 is equal to F times 0.25 plus 12 times 0.1. We're going to take the 12 times 0.1 to the other side by subtracting it. Divide both sides by 0.25 gives us F is 4.2 newtons upwards. So because it came out as a positive number, that tells us we got the direction of F right to start with. Okay, so one final question. So we're going to hang masses on it this time. So again, have a go at drawing a diagram, have a go at calculating it, and then we'll have a look through the solution. Okay, so those are just a few examples of moments type problems that you might come across as part of this topic. At this point now is a time to look back through these worked solutions and make sure you can explain everything that's happening as part of the stages of calculation. Because if you can't, then it's time to re-watch that section of the video. If you can, that's great. You've finished looking through these problems, and I hope you found that useful to your understanding of moments. If you have any questions, please feel free to comment and ask me. I'll try and get back to you as quick as I can, but thank you for taking the time to watch.